Hello, how are you? Following the last video regarding directional derivatives, I'm going to talk about gradient and its relationship with directional derivatives. Gradient represents many applications in physics, and for a few seconds I'm going to leave it off my lectures and I'm going to talk about directional derivatives. Then I'm going to tie its relationship with the gradient, and we're going to talk about the definition of the gradient in a few minutes. In last video we talked about directional derivative of a function of x and y is equal to the partial derivative of the function respect to x times cosine theta. That cosine theta represented the x component of the unit vector in R2, not R3, R2, plus the partial derivative of y sine of theta, and that's also this is the partial derivative with respect to y, and that's the unit vector right there. As you see right here, you see the sum of two product. And you know the sum of two product is going to lead to a scalar quantity, to some numbers. That number could be a positive or a negative. It could be a 0 too. Therefore, in order for you to have directional derivative, the existence of the partial derivative with respect to x and partial derivative with respect to y is essential. If one of them is undefined, you cannot find the partial derivative. Okay, and I talked about the partial derivative is going to be a scalar quantity. We also remember a few weeks ago we talked about the dot product of two vectors, like 1 and 2. When you dot it with another vectors of -3 and 5, the dot product of two vectors will also become a scalar quantity. Maybe I can write the directional derivative as a dot product of two vectors. Therefore, maybe I put partial derivative of respect to x and partial derivative with respect to y as a vector here and dot it with the unit vector cosine theta and sine theta. And this is nothing except your directional derivative of the function at any point x and y. A student going to say, well, I already know that, why should I know this? Remember in mathematics, when you have a polynomial equation, which is like this, it is very helpful to solve that equation to write it as a product of two factors. Then we can find the roots of these equations. Maybe the zeros of this equation is not a function, the roots are the zeros right here. No, I'm sorry, the roots of the equations, and if it was a function, we call the zeros of the function. Maybe here I'm going to break down the directional derivatives to a dot product of two vector. Maybe I can get into something to be able to help me to comprehend directional derivative more. Okay, let me write an example right here and say I have a function of x and a y. I'm going to write it a simple function like xy plus 2x minus a 3y. And you are standing on that surface at the point of 1 and 1, which is your x and a y. And you know when I put 1 and 1 here, my z is going to be 1. This is 2x, 1 plus 2 is 3, 3 minus 3 is a 0. I'm going to put minus 4y right here. That's make it 1. That's make it 2 is 3. 3 minus a 4, your z is a -1. Therefore, at the surface, you're standing at that point. And I would like to know at that point, if you travel in the direction of these vectors, and that vector is 2 and 3. What is the rate of change? Therefore, this is my vector v. I'm coming in that direction, and I want to know the directional derivatives, and I want to know the rate of change in this direction. And remember, sorry, the directional derivative at that point, the minute you leave that point, your rate of change, you might switch your direction to another direction. Therefore, directional derivative only provides you with the rate of change at that point only. The minute you leave that point, I would not guarantee that the rate of change of that point stay the same for the point after that or before that. Okay, I want to know what is my directional derivative of the function at the point of 1 and 1. Therefore, I want to know the partial derivative respect to x. This is y. And this one respect to x is 2. But I need a unit vector right here, which is cosine. Cosine is x over r. Your r is x squared plus y squared square root. 4 plus 9 is 13, is 2 over the square root of 13, plus partial derivative with respect to y is x minus a 4, x minus a 4, and 3 over the square root of 13. At that point, your x is 1, y is 1, your x is 1, y is 1, and the rate of change at that point is 6, and this is 1 minus 4 is negative 3. Let's make it a negative 9 over the square root of 13, and that becomes negative 3 over the square root of 13. At that point, your rate of change is going down, and if this one, you assume this one is pretty much 4, that become negative 3 over 4, or some places between negative 3 and between negative 0.5 and 75, some place in the negative side. But the question is here, you are standing at the point of 1 and 1, and you're going to ask me a question. Yes, you told me go in the direction of 2 and 3. In that direction, this is the rate of change. Then you're going to say, sir, what happened if I go that direction? 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 I have infinitely many directions, and I promise you, among all these directions, there is one direction that the rate of change is going to be the highest. Therefore, if you are depositing money in the bank, you want to deposit it in the direction that the rate of return is the highest. Or if you're going to borrow money from the bank, you want to go in the direction that the rate of change is the lowest. Then I'm going to talk about which direction provides you with the highest rate of return and the lowest rate of return. Okay, let's talk about that one. Maybe somebody said, well, what happened if the direction become, instead of this, become 1 and a 0? 1 and a 0 is going to be in that direction. Therefore, the unit, this is already a unit vector. And this one, your cosine theta is, the cosine theta is 1 over r, which is 1. And this one make it a 0. Therefore, what you have right here, you come up with a 3. See, in that direction is way more than that one. Maybe on the direction of 0 and 1, which is go that direction, this become 1 and that become a 0. Therefore, here you have negative 3. Negative 3 times 1 is 3. Therefore, and that direction and that direction are the same. I want to know the fastest one. Okay, let's talk about that. We said if you take your directional derivative and you break it down as the product of two vectors, f of partial derivative with respect to x, partial derivative with respect to y, dot with cosine theta and sine theta, and we had a function f of x and a y in a few seconds ago of xy plus 2x minus 4y at the point of 1 and 1, I'm going to ask you, for time being, ignore that. Let's only find out the directional derivative of f of x, y. Only find the value of that vector. The value of that vector is partial derivative with respect to x, which is y plus 2. And what is your y? Your y is 1. 1 plus 2 is 3. And what happens if I put partial derivative with respect to y? Is x minus a 4. X minus a 4, the x is 1, 1 minus a 4 is negative 3. And where is 3 minus 3? That's your 3. That's your negative 3. Ooh, in that direction. What is the magnitude of that vector? The magnitude of that vector f at the point of 1 and 1 is the magnitude of that vector, which is a square root of 18. Because 9 plus 9. And this is nothing except 9 times 2, which is 3 square root of 2. Remember, in last one, the highest one was 3 right here in that direction. It was 3 in that direction. It was this in that direction, which was 2 and 3. But look at that. This one got more. And a lot more. Can you find another direction other than 3 and negative 3 that provides you with the more rate derivative, with the highest rate of return? I'm going to ask you another one. What happens if I go in the direction of 60 degrees? Well, cosine of 60 degrees is 1/2. This is radical 3 over 2. But in here, I have an issue because here cosine is 1/2 and sine is radical 3 over 2. When this one is 3 and this is negative 3, when you take that number and multiply by any number between negative 1 and 1, this value is going to decrease. If you take this one and multiply by any number between negative 1 and 1, it's going to be way less than this. Somebody said, what happens if your partial derivative become a fraction like this? This is nothing except your partial derivative. But still, if I multiply by any number between 1 and negative 1, that's the proper fraction. Multiply by proper fraction, that becomes a 1/4. Multiply by this by that one, that becomes negative radical 3 over a 10th. Therefore, this cosine theta sine theta is one of the reasons that it reduces the magnitude of that vectors or reduces the directional derivative. Then from today, I'm going to say, if you have a directional derivative of f of x and a y equal to f of x, f of y dot with cosine theta, sine theta. If you ignore that unit vector right here, you ended up with a vector. That vector provides you with a direction, which that direction among all the direction around point 1 and 1 give you the highest rate of return. And that highest rate of return in physics called gradient. Then what is the gradient? Gradient is a vector. The gradient, it gives you the direction. But somebody said derivative should be a scalar quantity. The directional derivative is the magnitude of the gradient. Therefore, if you want to know the directional derivative of any function f of x and you want it to, a direction that provides you with the fastest rate of return, this is the direction of the fastest rate of return. But if you take the magnitude of it, that will end up with the derivative or directional derivative. Let's talk about this for a few seconds. Let's say your directional derivative of f of x, y is partial derivative of x, partial derivative of y, dotted with cosine theta, sine theta. If you remember, the dot product could be written in two different ways. If you had a derivative u1, u2, and you dotted with V1, V2, that was the same as the magnitude of the U, the magnitude of the V, cosine of an angle between them. Or you could say U1, V1 plus U2, V2. There are two different ways we could represent the dot product. Here, I can write that directional derivative as partial derivative of x cosine theta plus partial derivative of y sine theta, or the magnitude of that vector. I'm going to call that vector a gradient. That gives me the fastest rate of return. In gradient has a notation. The notation come from Hebrews, which called nabla. Nabla, it look like this, but in United States, pretty much this is look like a harp, and that's the you play music on it. Therefore, the symbol for harp represented the gradient. This is called gradient of the f. And if you take the magnitude of the gradient, that becomes the directional derivative of the function at the point of x and a y in the direction of the what? Fastest. Therefore, the gradient, which is a vector, gives you the direction, and its magnitude give you the what? Give you the directional derivative. Therefore, the fastest direction provided by the gradient f of x, f of y. Okay, somebody said, I don't want to write my directional derivative like that. I want to write it like this. Therefore, I'm going to call this one a gradient of f. I want to write its magnitude. This is a unit vector. I call the unit vector u, cosine of angle between them. You know that's the unit vector, and the magnitude of the unit vector is 1. Therefore, the directional derivative of f of x, y also can be written as the gradient of magnitude of the gradient times cosine theta. Okay. What happens if that theta becomes 60 degrees? That becomes 1/2. 1/2 is going to reduce the magnitude. What happens if this becomes 30 degrees? Radical 3/2. It's going to reduce it. What is the what theta could be that give me the highest value for that one? That theta should become 0 degree, because cosine of 0 degree is 1, and if the theta is 0 degree, this is nothing except the magnitude of the gradient. Therefore, if your unit vector, that's the direction, maybe the fire is burning, and also your gradient are in same direction, they are in same direction, that produces with the fastest way that the fire is either burning. But what happens if this is your unit vector and this become your gradient? The angle become 180 degrees. Oh, that become a -1. If this become a -1, the directional derivative is going to become negative the magnitude of f. That's become a smallest value. Therefore, the magnitude of the gradient give you the fastest rate of return. The opposite direction give you the slowest. Therefore, if you are at that point and this direction give you the fastest, this direction give you the slowest. If this direction give you the fastest, this direction give you the slowest. Therefore, from today, you're going to be asked two different questions. You're going to be given a surface, and the surface is x cubed y minus y squared plus 3xy. In here, they're going to say, if you're at the point of 1 and -2, what is point of 1 and -2? This is 1, and you're right here. I'm standing right here. I'm a firefighter. And I've just arrived at that point, and I'm going to ask the mayor of the city which direction fire is burning the fastest. Therefore, the mayor said, I don't know. I give you the surface. I gave you the point. You figure it out. Right away, you have to say the gradient of the function is 3x squared y plus 3y, and your partial derivative with respect to y is x cubed minus 2y plus 3x. You replace your gradient with the position the mayor gave you, and if the 1 is 1, square it is 1, 1 times 3 is 3, 3 times negative 2 is negative 6. And 3 times negative 2 is a negative 6. 1 cube is 1, minus 2 times negative 2 is a 4, and 3 times 1 is a 3. And this is negative 12, comma, 8. Then right away you have to tell the mayor, I got it, sir. If this become my compass, I have to come down 12 unit to here, 8 unit here. This is where the fire is burning the fastest. And I have to go ahead and put the fire down in this direction. And the mayor is going to ask you, can you tell me how fast the fire is burning? You better say the directional derivative of f at the point of 1 and negative 2 is the magnitude of the gradient of the f, which is equal to negative 12 squared plus 8 squared, and together is become 8, 228. 228 is close to 225, and a square root of 225 is 15. This is approximately 15.1 feet per second, because this is rate of change and it's a function of time, and this is approximately. You say it is fire is burning in that direction, and that's how fast it's burning. Therefore, if they ask you the fastest, you only have to do the gradient. But the mayor is going to say, I'm not worried about this direction. There are not many houses in that way. Let them burn. But I want you to go in this direction, which is 2 and a 1, because there is a lot of houses in here, and tell me how fast the fire is burning in that direction. If you want to know the directional derivative in the direction of at the point of 1 and negative 2, and go in the direction of 2 and a 1, this has to become a unit vector. Therefore, your unit vector is going to become x over r and y over r. Therefore, in here, your directional derivative is going to be f of x cosine theta. What was partial derivative with respect to x? Negative 12. Negative 12 times 2/5. Plus, what is the partial derivative with respect to y? It was this, which is 8 times 1/5. The direction the mayor told you we have many houses is going to burn at negative 24 over 5 plus 8 over 5, and that's become negative 16 over 5. Therefore, you have to say, sir, in that direction, the rate of change is negative. It's not really burning fastest, because for every 5 seconds, the fire going down by 16 feet. I'm sorry, the rate of, for every 5 thing, I shouldn't make that example, but for every 5 unit you go right, it go down 16 unit. Therefore, you do have to know from today, gradient does have a relationship between directional derivative. Gradient give you the direction, which is a vector, and it give you the direction that it either increases or decreases, the fastest or the slowest. But in any other direction, you have to take your gradient and dot it with a unit vector right here, dotted with a unit vector. That becomes your directional derivative right there. Please remember that when it comes to R3, like if you do have W equal to x squared plus 3xy plus 5zx squared minus yz. And yet, is this one has the gradient? Yes, it does have a gradient. And the gradient is partial derivative with respect to x, which is 2x plus 3y plus 10zx. And respect to y is going to become 3x minus z. And respect to a z, it has 5x squared minus a y. Yes, you do have a gradient, but that gradient cannot be applied to a directional derivative, but you're going to have another application in R3. Therefore, yes, you cannot use the gradient from R3 to represent the what? To represent the directional derivative, which is in R. This is R4, this is R4, this is R3. R3, your domain is in R2, but your R4, your domain is in R3. And that's the end of the video. And next video, I will gonna talk about more about the gradient and how the gradient can be used to write equation of a line, normal line, and equation of a tangent plane, and what is the relationship between the gradient and the surface itself.